Hello and welcome to my video presentation for the 2023 Energy Simulation Summit. My name is Gordon Meehan and I'm a master's student in chemical engineering at the University of Calgary. My thesis supervisor is Professor Roman Shore. My presentation is on the numerical model development of a coaxial closed-loop geothermal system. First, I'm going to discuss the background to this project. The University of Calgary is looking to replace the existing natural gas plant used for campus heating with a renewable alternative to meet their goals of carbon neutrality by 2050. Low-temperature geothermal energy has minimal carbon emissions and can be exploited for district heating, which makes it a prime candidate for the replacement. Conventionally, geothermal energy has been exploited by producing hot fluid from a geothermal reservoir. By using a closed-loop coaxial design, the well can be drilled into formations with little fluid and little permeability. These closed-loop designs require no fluid travel through the formation or formation stimulation, which avoids issues such as cold fluid breakthrough or induced seismicity. Lastly, the coaxial design over a U-loop system reduces drilling complexities. Here are the main purposes for developing this model. Global climate change is causing catastrophes worldwide, and the University of Calgary has pledged to attain net carbon neutrality by 2050 in response to this. By replacing the cogeneration natural gas heat plant at the end of its life with extremely low carbon emitting geothermal heat, the university will be closer to achieving this goal. And lastly, by developing this model, I can enable an optimization of parameters to ensure that the best system is proposed. Here is the method that I used for developing this model. The design was modeled using COMSOL Multiphysics 6.1. The inner piping or the tubing was built with the pipe walls and the annular space in the reservoir built around it radially by means of 2D axisymmetry, which it's shown in the top radial or aerial view on the slide here. The non-isothermal flow was modeled using conservation of momentum and heat equations in steady state conditions, as shown in the next slide. The produced fluid's temperature was measured at the outlet of the tubing. Here are the previously mentioned conservation of momentum and heat equations, as well as the conductive heat flux equation for the heat transfer within the formation. The terms and symbols are described as well. And lastly, I've listed out the boundary conditions. The geothermal gradient is the average for the Calgary area. Some simulations were run using an additional 2,000 meter long vertical, while others were just 2,000 meters some simulations were run using an additional 2,000 meter long horizontal, while others were just 2,000 meters vertical. And then lastly, the fluid that I modeled was water. The preliminary results are shown in the graphs here. They show that the flow rate directly affects the thermal output. This effect is more pronounced in the horizontal scenarios than the vertical, which is to be expected because when the fluid is in contact with the warm rock longer, there's more opportunity for energy transfer, as is the case when it is moving slower or traveling the extra length of the horizontal. A similar model was developed using CMG by Anne May, a postdoctoral research associate at the University of Calgary. At 500 cubic meters per day, the models give a similar output as can be seen in the graph here, but there is a growing discrepancy at higher flow rates. The next steps that I need to undertake in developing this model would be to vary other parameters such as the casing tubing diameters. A reason must be found for this discrepancy with the CMG results, and it'll also be necessary to make a time-dependent version of the model to fully understand the seasonal and diurnal effects on the input. Thank you so much for watching my poster presentation. If you have any questions at all, please reach out to me at the email listed here.